Okay. It's already broadcasting in YouTube, so we can start the seminar.
Okay. Good. So I think you can see the screen now, the slides. So yeah, I would start. So hello everyone. Welcome to this 15th session of the ISRM Young Members Seminar Series. My name is Alessandra Insana, and this evening for us in Europe, together with Dr. Philip Brown, we are going to chair this 15th event of this seminar series. So we are very happy about this. Let's see if I can go on. Okay. So first of all, some acknowledgements. Some acknowledgements to you who are attending this event, of course, and also an acknowledgement to the International Society of Rock Mechanics and Rock Engineering that provides the support for this event, and in particular Yanni Maritz, Muriel Gasque-Barbier, and and Esteban Ormazabal, ISRM Vice President, respectively, for Africa, Europe, and Latin America. They are the chairs of the ISRM Young Members Committee. Of course, also thanks to all the other young members that are part of this group from a number of countries all around the world, Spain, Chile, China, Japan, Australia, Canada, just to mention a few. Of course, we welcome our speakers. So thanks to all the speakers that agreed to be here today. I'm going to unveil already their names. So Dr. Elham Mahmoudi, then we will introduce them better, of course. Dr. Manuel Alejandro González Fernández, Dr. Etienne Lavoine, and Jorge Terron-Almenara. So thank you for giving your availability to present your work this evening. Before we get into the talks, we would like to provide a brief introduction and some key information about these seminars, this event, whose aim is to let's say, create a network among not only academics, so students, researchers, but also engineers, so practitioners, to share knowledge, ideas, experience in the field of rock mechanics and rock engineering. And also to strengthen the connections among different countries. This event more or less are held 4 times per year. There are some criteria to be a speaker that you see listed here. So you need to be an ISRM member, to have a maximum age of 35 years or 40 years if you got a PhD degree in the previous 5 years, and to have worked in rock mechanics and rock engineering for a period no longer than 10 years. So these are the criteria. How to be a nominee? So we accept self-nominations, or another option is to be nominated by your national group or by someone or some organization that is acquainted with the nominee's work. And for the nomination, an email has to be sent to suggest a name to this email that you see here on the slide. Now, some housekeeping rules. So the idea is that this evening, as we anticipated, we will have 4 talks. Each will be around 20 minutes long, with a question and answer session of around 5 minutes. And you are asked during the presentation to turn off your camera and microphone. And then during the Q&A session, if you have questions, you can type it in the chat or you can raise your hand. So I would say that we can start with the first speaker. So I'm really happy to have with us this evening Dr. Elham Mahmoudi. So she's a researcher and consultant at Deltares in the Netherlands. Her specialization is in the numerical simulation of geotechnical problems, reliability-based analysis, and machine learning. She got her master's degree in 2012 from IKIU in Iran, with a thesis focusing on numerical modeling of underground pipelines crossing active faults. Then she moved to Germany, where she got her PhD under the supervision of Professor Tom Schanz. The PhD topic was on the probabilistic analysis of underground energy repositories, and she got her PhD with distinction. In 2016, she joined the chair of computing in engineering as a senior researcher, working on system adaptation and parameter identification in mechanized tunneling and subsurface modeling. And then in 2023, she became a risk and reliability expert in geotechnics at Deltares, focusing on reliability-based design for flood defense structures and railway embankments. So today, Dr. Mahmoudi will give us a talk entitled Probabilistic Analysis of a Rock Salt Cavern with Application to Energy Storage Systems. And I'm very much looking forward to hearing to this talk. So Dr. Mahmoudi, the floor is yours. I will stop sharing now. Yes, and you can start sharing your slides.
Thank you, Alessandra. I hope now the sharing works.
Not yet.
Not yet. Okay, let me try again.
Now
And
it's coming. Yeah, perfectly.
Okay.
Thank
you very much for your nice introduction. It's quite nice also to look back in short sentences, and I'm very happy to have the opportunity to introduce some of the work I have done in my PhD to the group of ISRM. And this is the work that I have done in my PhD, as I said, on rock mechanics, but not, I would say, common rocks, but rock salt cavities, where the storage of the renewable energies is a topic, and rock salt has been identified as the best place and the most environmental friendly place for storing energy. The idea is that renewable energies in production, normally they have the fluctuations that it's completely different than the fluctuation normally the demand side of the network has. It means that during the nights, for example, we have better winds in the North Sea in Germany, then more production than needed, and during the summer also we have less wind, but we need more energy. And there are ideas about how we can make some storages of this energy, this excess energy, to shaving out these fluctuations and making the optimal use and resource of the energy network. So one of the idea is that to put this energy in form of compressed air or converting this energy, let's say, to hydrogen, and store them underground in some abundant cavities, which have been used before for the oil and gas storages, or also they have been used for storing some nuclear waste, for example, or even just for taking out the salt from the salt mines. And this is especially known as it is in use in Germany and also in Canada, in Netherlands, in many countries around the world. This formation of rock salts are available, and they are also bringing to the picture a very good, nice let's say, less permeability. So you do not need any lining. You do not need any also heavy drilling for reaching out, because it's very easy of solution mining, let's say, because you put the water in and you get the brine out. So you get a cavity. Usually speaking, it seems easy, it seems very feasible, it seems also very usable in the community when environmentally look at it, but it comes with a lot of of course, engineering challenges. When we are speaking about putting the renewable energy inside of these cavities, it means that during the time, which means also during one day, we need to do the loading and unloading several times. We have at the moment the cases that one loading and one unloading is happening during one day, and also seasonally that can change. The other problem with the pressure, that you pressurize and you unpressurize the cavity, is with the temperature, because this the gas that we are going to store in these cavities is compressed, so it gets a higher temperature by loading and less temperature by unloading. But the rock salt, as a viscous material, it's very sensitive to the temperature, and it can show some movement and some deformations by this loading and unloading, and also with the changes in temperature. So it means that we need to tackle the problem in different sides, in different aspects. Let's say we do not know explicitly how the material react to this type and this regime of loading and unloading, which is cyclic, but it's not cyclic with the higher frequency more than 8 hours. And also it is cyclic not just in the direction of the mechanical, but temperature also is changing. That's why we in the bigger group of the research, we have made an experimental investigation as one important pillar for the project, and we said that some PhD shall work on how a triaxial cell and also a creep test can take place over the samples of rock salt. The other aspect is that, okay, we can see them in the experimental hole, but we need also making some numerical model out of it to be able to predict the behavior before putting these compressed air or hydrogen inside the cavity. That's why we thought about constitutive model developments also. Another PhD has been assigned for developing a constitutive model which is able to consider all of these aspects that I was speaking about. The last part, of course, is about analyzing the system. The model shall be analyzed. And when I'm speaking about simulation, it's not just simulating the behavior in a finite element code, of course, including that, but also we were concerned about the parameters and also the ideas of uncertainties that I will speak about that a bit more extensive today. Because I was the PhD who did the last part of the job. And of course, there were some loop in between all of these three. You can imagine without the constitutive model, no simulation can happen. And also without the first simulations, we couldn't run the correct boundary conditions for our experimental device. If we wanted to go through the experimental work that has been done, I just brought some bullet points here. It's not my job, and I just also put the name of the colleague that done this experimental work, quite extensive, but also challenging. You can see that, as I said, high pressure is here, is higher than normal pressure that we are in geotechnic working with, and also cyclic mechanical and temperature loading and coupled thermomechanical loading shall be done as well, because at the time of mechanical loading, the temperature also with a small lag shall be increased and decreased, and it's not just the cyclic loading, but also cyclic and creep tests, which is quite time consuming. The other aspects about the rock salt cavities, as I said, they have very low permeabilities, but they're still under the certain stress strain conditions. You may get the the cracks in the model in the rock, and these cracks, of course, are not desirable because they can lead the gas out and make some leakage, but we are fortunate because the rock salt is showing some viscosity and healing also properties, which means that after a certain amount of time, every the damaged area, or let's say every crack, is tending to be closed also by time. There are a lot of, I would say, investigations are also going on that, but we were in the first steps of doing the experimental works on that, also to see how they will develop and how they will be closed. So this is the apparatus that you can see here, the schematic, and also the shape that has been made in the lab, but I will not go through the details of that. Just mentioning here how I provided some information for this analysis was that I had the numerical analysis, and I made some first preliminary work to see that how the stress paths look like when we are loading and unloading the system, and also in different areas around the cavity, how the stress path is different in different areas. So we could give this as a boundary condition to the device, and asking the person who was responsible to simulate or trying to simulate this stress path. Here also you can see how the rock salt look like, actually very crystallized, but from different areas from Germany. We got different samples, but this one that I show here is from Sondershausen mine, a salt mine in Germany, where we could get the data from 500 meter underground. So it's not normal geotechnical depths of excavation that I'm speaking about. Moving forward, I told you about the constitutive model and how and why we need a constitutive model. Actually, I tried to put them in these three pillars, that why a new constitutive model was needed. Because beforehand, we had some constitutive model that they are working for the creep, of course, and they are working, some constitutive model can also model damage in the elastic behavior and cyclic behavior. Also, there are constitutive models that they can work on their for the viscoplastic materials like rock salt. But all in all, there was a lack of that. And you can see we have different also loading conditions in such cavities. So we had to consider a new constitutive model, which is a part, a combination of the other available one, but it came also with its own, let's say, development works and challenges, because we wanted to know about the fatigue after cyclic loading. At the same time, we wanted to know about the creep behavior, because we have the constant loading during every 8-hour shifts, or if is it about the hydrogen, even longer shifts for constant loading. So the creep may happen under that loading, and of course monotonic loading during the charge and discharge the cavity was the let's say boundary conditions that we had. Here is the creep behavior. I assume many of you have seen around this graphs, that firstly we have a tertiary and then a transient, and then a steady state, and of course afterwards tertiary creep. What we focused on was the steady state creep, because we considered the transient part also in the monotonic loading part, which is coming with the viscoplastic modeling, and the tertiary we modeled with this elastic part when the damage parameter has been considered. So let me just jump over some of the slides. Otherwise, my time would be very, very limited for the part that I'm more interested to show you. This is also about the fatigue part of cyclic loadings. I also put here the dilatancy and failure boundary of the model, which at the end has been developed by my colleague González. And we worked in this model in a direction of having firstly the basis of a viscoplastic model, which called the Psi model, and of course one very important aspect about the rock salts is this volumetric changes, a volumetric change in the volumetric strains, and we have, after a certain boundary, we have dilative behavior. So this line of green line here, you can see that how the dilation and the compression zones are different here. After anything after the under this line is compressive. So always in the community, in the practice, they wanted to stay under this line. Of course, there are cases that the stress passes past it and going to the dilative zone. So that is when the damage also come to the picture, and the cracks are getting to started. But let's say we have the model and some checks with the different studies before in experimental facilities around the world. We checked also this model, and the implementation of the model has been done by Cavern also. And I tried to help with this, with the parameter identifications and so, but we will speak about that later a bit more also extensively. This is how I started to modeling the cavity. This is the area that the cavity is normally taking place. Let's say for this Sondershausen case, it was almost 500, more than 800 meter under the ground, 500 meters of overburden, but also some excavation happened actually at the 800, and the rock cavity, it has the 233 meter of height, or let's say is going deep. And this is the cavity that simplified, of course, by the shape, but the shape almost the same. It's not that much irregularity, but maybe in the bottom side there are some irregularities. Also, we did some studies with master students on that how they can be affecting the stress distribution. Quite interesting work, but unfortunately I cannot share it with you because it was in the contract with some companies in Germany. Anyhow, let me bring you here also with this 75 meter of diameter, and this is the model I made. It's an axisymmetrical, the numerical finite element, which different point around the cavity were point of interest for us. Always the points that they are more concerned in the practice about are the points that in the top, because there are very high rate of leakage in the, let's say, N1 point. That's where all the pipings from the top is working, and because of all of those connections, there is always a damage zone in that area. So the other point, which is of course more interest, and there is a vulnerability for leakage, is this point that the 1/3 in the bottom, because here the higher pressure is applied, and also there are this possibility of having the brine and also some fallen part of the rocks to this area. So these two areas actually are the most vulnerable, but I will speak mainly today about this N4 area. Because the pressure was firstly our concern. The area of N1 is something that is more of interest of how to do the job of connections and installations and what they call the casing shoes when they are doing this drilling. For how it's happening, actually in the practice, as I said, the solution mining is the way that they are drilling this. There is always a cemented casing which is drilled, like what we are doing also in the oil and gas industry. So they start to injecting some water, just let's say water from the rivers, and they are start this injection. So some leaching is happening, and then by bringing up the jet of water, you get the final picture like this. After that, they also start to inject some gas with higher pressure than the brine, so they can extract the brine out of the cavity, because beforehand it was with the brine. And then when it is filled with that gas, then they can pump and pumping out the resources that they want to store in it. Either is it natural gas, or beforehand previously it was mainly natural gas, but nowadays, as I said, they are more interested in compressed air and also hydrogen. And of course, after that, this charge and discharge is happening, which is mainly the cyclic part of the job. So this is how the loading during the time has been modeled, simplified, of course. And this is the PI that you can see here I applied. This is the graph for that. Important for the people in practice is always that how much they are allowed to come down in this graph. Let's say this P mean value is always point of interest for them, because they want to know that how less can be stored in the cavity. And this is something very interesting about the rock salt storages, because normally if you are working with the tanks or any other type of, let's say, storages, you are obviously thinking about how high is the capacity and how much pressure I can, or temperature also I can apply to the system, because the walls or the let's say the boundaries can take. But here specifically, the case is that the minimum is also important. Why is it so? Because as I said before, rock salt is showing some viscosity, and without any loading from inside, the hydrostatic pressure in the body of the rock mass is high enough, and with time, of course, the viscosity will force the cavity to be closed. And this is what is happening really also in many different areas. In France, they had this this problem, and they learned by doing several times ago that, by time when they didn't apply enough and optimum minimal pressure, so they got these cavities completely or partially closed, actually, which is not what they want, because, of course, if the cavity volume is decreasing, you cannot put the volume that you want storing in it. And of course, it's making the job again and again. You have to do the excavation somewhere else, which is not something desirable, let's say. So what we can see here is that I have tackled the problem in several ways. One is that we do not want to have that problem of having the dilative behavior, let's say staying under the dilatancy boundary and staying in the safe zone, because we do not want to get any upper cracks. Also, we do not want to have any volume loss. This is another problem, which is serviceability problem. Both of these problems need to be solved and need to be considered in the reliability cases. I have to go a little bit faster and showing you how I considered the the parameters for this analysis, because then the parameters are not very certain for us, and there is a high range for all of the parameters involved, and we are speaking about more than 30 parameters here. All of them needs to be identified, and for identifying these parameters we did some sensitivity analysis. This sensitivity analysis is something systematic and global, because all of the parameters also were correlated somehow with each other. And after that, we considered some reliability-based aspects to be informative for the client, for the operator, that in taking these values that we are delivering to them, how much of chance they are also taken. They were interested on, as I said, serviceability and also stability at the same time. So they wanted to know that how much of the values for the minimum pressure they can apply. So I had to come up with some concepts in reliability, which is able also to do the calculation very fast, because if I want to go the Monte Carlo calculation, 10,000ths of the calculation was needed, and every of the finite element calculation with this extensive constitutive model taking me more than 1 day. So I could not afford that, and I came up with one substitutive model idea, and also some more advanced reliability analysis idea, which is here shown at the subset simulation. But let me go faster over this. Of course, you can find some of all of this information in the papers, where we got some data like this for the practice. When I applied the reliability for the specific type of structure, index of reliability, and then I could say how much of the pressure the practitioners in the site should apply, then staying safe. This is how our journey started, from very specific questions, ended up with some data analysis and probabilistic analysis. I hope you got some ideas about the job. It was not very detailed, but I assume that if you have any more questions, I would be happy to answer. Thank you, Alessandra. I think it's time.
Yeah, thank you very much, Elham, also for respecting the time. So I'm sorry, but
No.
yes. So, well, thanks for the wonderful overview of this work that included numerical modeling. You also gave us an overview of some experimental results, and also constitutive modeling. So really a complete overview. It's also nice to see how rock mechanics can help providing answers to the challenges of our century related to energy. So it's a very interesting topic. Yeah, so thank you very much. So I think it's time for questions for Elham. I don't know if anyone has any questions. So as we said, you can either raise your hand, write in the chat, maybe also on YouTube. No, I don't know. Those who are attending there. Please. Yeah, Philip.
I have a question. Thank you for the nice presentation. I was interested in the constitutive models that you use for cyclic behavior. So what kind of model do you use to take into account the cyclic deformation of the rock in particular?
Actually, the model is mainly an elastic spring, let's say, which is taking care about the accumulative strength also. And we added one damage parameter at the end. So we're counting for the energy that is in the strain by every time the strain happening, and then we calculated if is it more than one specific value, so the energy is expended to be a crack. That's very simplified, but I would say that because of all the other uncertainties, we were not that much interested to go further with developing the physical model.
Okay, thank you.
Also, I'm not that well equipped about that, but I can tell you about this, that the part of elastic and also damage based on the accumulative strain has been added.
Okay, that's clear. Thank you.
Thank you. Any other question? Well, maybe I can ask. Maybe someone is showing up. No.
Yes, I have a question, but I don't know how to raise my hand. I'm sorry.
Just
And
go
it
ahead.
seems that my camera is now working. Congratulations for the presentation, Elham. I just have a small question regarding the, for example, in the northern Netherlands, there are different type of, I would say, different slenderness caverns as those coming from the exploitation of bischofite and other salts. What's the potential of those, if there's a potential for energy storage of those kind of caverns? Because those you showed on your presentation are like a penny shaped or cylindrical or slender caverns. Is there any potential for those
Yes,
flat
actually,
caverns or?
yeah. Actually, these shapes that I showed, they are, let's say, the fantasy. If some country can afford them, they are perfect ones, because also they coming with a very high salt formations, and they are not very common, unfortunately. There is always some layers in between,
Yes.
which is exactly. Which is interrupting, and so we have to stay in a shorter height. So also we go a little bit in the shape of, I would say, a tulip or a tulip. that's the main common shape that in France they are doing, and they have always this. I would say they are jealous with the Germans that they can apply this one without any problem in the practice. But you're right. I mean, there are the less amount of the height with the, and this is the formation of salt, that it's not a dome, but it's just layers of salt. But also they are possible to be used for this type of activity.
Okay, thank you.
Yeah.
And congrats again for the interesting presentation.
Great. There is another question for you, Elham. So please, Ailie Seraza.
Hello.
Hello.
Hi, my name is Aili. I am from Kuala Lumpur, Malaysia. Question to the speaker. Based on I'm very interested to look at your presentation, which highlight the constitutive modeling. And since this is rock, since this is looking at formation of salt, is it possible if we were to model the constitutive model by using the Chemclay model?
Clay model is not possible for this because the viscosity there is not that much, but of course we have the hardening parameter there. I know where you come from, the hardening is there, but when we tried that, because this continuum formative of the soil here, of the rock here, is completely different by those in the Chemclay considered. We did not convince firstly to use that hardening, but of course the same cap is applied for the part of the viscoplasticity, and there is nothing about the creep behavior. Anyhow, you have to also, if you get the Chemclay as the basic for the viscoplastic part or the plastic part, even you have to add the creep part and of course the damage part.
Okay, so if I understand this clearly, if I were to model it using Chemclay, I just need to kind of like tweak the model to represent the rock behavior more correctly, rather than just taking the original Chemclay model. Is that right?
Yes, and this is also happening here because we have used one, let's say, existing model for the viscoplasticity, and we added the part of the creep model. When I'm speaking about adding, then it means that your potential surface needs to be changed also. And of course, we had to change the potential for getting the everything in the compression zone, just following the creep behavior. Otherwise, everything going down to be one node.
Understand. Thank you very much for the clarification.
Quite interesting question. Thank you.
Great. I think it was a very lively discussion. I'm very happy about that. So Elham, your talk really raised many questions. I think we need to move on. So thank you once again. So now let me share again the screen just to present the next speaker. Let's see if it works. Okay, I think it should work. So let's present the next speaker. So we move to Dr. Manuel Alejandro González Fernández. So a brief bio. So he graduated as a mining engineer in 2012 from the School of Mining Engineering at the University of Vigo in Spain. Over the years, he gained experience in various industries. He worked in the metallurgical sector as the head of the R&D department, in the food industry as a production manager, and in construction as a project manager during the development of a photovoltaic farm. In 2019, he joined the University of Vigo as a researcher at the Department of Natural Resources and Environmental Engineering. And in 2024, he obtained a PhD in rock mechanics, so this year with a PhD thesis focusing on the scale effects on hard rocks and the study of transversely isotropic rocks. So his talk today will be entitled Size Effects on Strength and Deformability of Intact and Artificially Jointed Hard Rock Samples. So please, Manuel, you can share your screen and start. Thank you. Okay, it's not yet in presentation mode, but now it is. Perfect.
Presentation. Okay, perfect. Thank you for the kind introduction, Alexandra. I'm going to talk about the size effect on strength and deformability of the intact and artificially jointed hard rock samples. That is part of my thesis. Due to the extension of my thesis, I only focus on these two parts. So we start with the intact granite. I have divided this presentation in this part in 7 different parts. So let's start with the objectives. The main objectives of this presentation, of this part, are examine the size effects on the models UCell and UCell, evaluate the applicability of these two models to the Cavern value criterion to introduce the size effect on the criterion, and search for the scale effects on the brittle ductile transition and the frictional behavior, and to conclude, evaluate the failure mechanism with the confining pressure and the scale effects. So let's begin with the introduction. So what was the reason to look into the scale effects on triaxial tests? The laboratory that I used to belong at the University of Vigo has performed a past study on the same rock, granite Blanco Melo. It was, in this case, a study made on UCS tests. So they found that there were an ascending descending trend of the peak extent with the increasing diameter. This trend doesn't fit with the typical descending trend with the incremental diameter. So we decided to perform the same study, but in this case, we extend it to a triaxial compressive test. So we use the same granite as the past study. This is, in this case, the Blanco Mera, which the composition of this granite is 20% of quartz, 35% of plagioclase feldspar, 27% alkali feldspar, muscovite, biotite, chlorite, and sericite. Regarding to the grain distribution, the distribution is scattered with quartz grains ranging from 1 to 6 millimeters, feldspar crystals ranging from 1 to 3 millimeters, and smaller micas. So we decided to use for this study 4 different diameters. In this case, 84 millimeters, 54 millimeters or NX diameter, 38 millimeters, and 30 millimeters. During the test, we also measured then the deformability using 2 different methodologies. The first one was the measuring with LVDTs, the plate-to-plate distance, and we also measured the deformations with axial and radial strengths. This is not the main what can I say, the objective of this part of the study, but in the future we will see what was the reason to measure the deformations. So here we can see the triaxial testing system with a load framework with a capacity of 2000 kilonewtons, a fully servo control system, the data acquisition system, and the system who give the confining pressure to the hook cells. In the right, we can see here the different hook cells used in this study and the corresponding sleeves. So now here we can see all the tests performed in the whole study in the granite, both intact and jointed. But here we only focus on the intact ones. We performed 97 different triaxial tests for intact. And at the right, we can see the typical triaxial stress strain graph, where we can see the curves of stress strain, the radial and the axial, and how the parameters were derived, the peak strength and the residual strength in this part, and the elastic parameters for the part that we will be seeing in the future. So here we can see the average values for each diameter and confining pressure obtained for the test for the peak strength and the residual strength. If we have a quick look for the peak strength, we can see that the values of the peak strength increase when we increase the confining pressure, something that also happens in the residual strength. Also, at lower confining pressures, we can see that there is this ascending descending trend observed in the UCS test performed in the past study. This trend is less visible in at high confining pressures. For the residual strength, we can barely see this ascending descending trend at lower confining pressures, but it seems not to be a scale effects on the higher preservance confinements. So to analyze the results of time, we decided to use 2 different methodologies. The first one was the universal size effect law that consists in 2 different parts. The first part is the descending trend that was proposed by Bazin, and it's called the size effect law. And the ascending part is also proposed by Bazin, that it means the fractal fracture size effect law. So the value of the strength will be the minimum value of at each point of the 2 of the SEL or the FFSEL. And we also use the improved version of this universal size effect law, the improved universal size effect law, which consists in also 2 different parts. The first one, proposed by Carpentering, the multifractal scaling law of or MFSL, that is the descending part, and the ascending part is a modification of the previous proposed by Bazin. This modification was performed by Masumi, and it's called the modified multifractal scaling law, or MMFSL. So, like in the UCL, the value of the strength will be the minimum value at each point of the 2 MFSL or MFSL expressions. So here we can see a fit of the values obtained for the test for 2.5 megapascal of confining pressures. And we can see that both models, the UCL and the improved version, fits very well with the results obtained and mostly overlap the results of the 2 fits. So why we decided to use the improved version and not keeping the original version? This happened because when you make the fit for larger diameters, the original version, the UCell, it tends to be 0 at the larger diameters. That is not the reality. We know that a rock mass with an infinity diameter, it has also a strength. So the improved version is that when we tend to large diameters, it tends to constant value that it's matched with the reality. Also, we decided to introduce the site dependency on the Hochbrand criterion, and we start with the Hochbrand criterion, and we change the values of the strength with the values of the strengths proposed by the UCell and the UCell. If we perform these changes, we obtain the 4 different curves for the different diameters. And we can see that for all diameters, the correlation obtained through the both versions, the UCell and the improved versions, are very good. And also we can see that it doesn't matter which version we use. The values obtained for the original version are the same as the ones in. So let's move to the site dependency, to the frictional behavior and the brittle to ductile transition. Here we can observe the brittle to ductile transition through the transition index. This index ranges from 1 to 0. It means when this index is close to 1, it means that the rock is brittle. So we can observe here that our rock used, the granite, is very, very brittle. This because it's close to 1. And we can see here a transition to a more ductile behavior with the increasing of the confining pressure. Also, we have measured the shear band angle of all the tests performed. Clearly, the shear angle of near 0 confinement pressure were impossible to measure. And we observe for all the diameters used that the shear bar angle decrease with the increasing of the confining pressure. So with this data and with the expression of the shear stress and the normal stress, we can plot the friction coefficient both for the peak and the residual strength. So we can obtain the values for each diameter. And if we plot the friction coefficient against the sample diameter, we can observe also for peak and residual peak and residual. We can observe this ascending behavior observed in the strength. Regarding to the failure patterns, we can find for long confining pressures axial splitting, moving through a mixture of axial splitting and starting shear banding for mid confining pressures through a full shear band pattern file. So we move to the next section, that is the section of the fissured granite. It's also divided in 7 different parts. So which were the main objectives? The first one was examine the size effects on the fissured granite samples, examine the size effect on the confining pressure on peak and residual strength, examine the size effect of the degree of jointed on the peak and residual strengths also, and examine the size effect deformability of the joint samples with the elastic parameters. So in our laboratory, we have performed in the past a study with the same granite also, the granite Blanco Mera, a jointed test, but they were only focused on NX diameter of 54 millimeters diameter. Why we performed this study on a hard rock? This was because there were not many studies on jointed samples, and the studies were based on artificial materials like cement or plaster, or soft materials like gypsum. So our laboratory decided to perform this study. And we make another step to see the scale effects on jointed samples. So I'm going to explain briefly how the samples were obtained. Here we have the typical block for a sample obtaining, and we mark the subvertical joints. Then we cut it using a saw, and then we clamp together to process to drill with a core driller. Why we should perform this first? If we obtain the core first and then we perform the subvertical joint, we obtain a reduction of the diameter of the sample. So this sample will not be usable to obtain results. So we obtain the cores that here we can see the subvertical joints, and we use electrical tape to grab the core and cut the endings to obtain more or less the length of the final sample. We proceed to grind the ends to obtain a smooth surface, and then we secure this sample to a 3D mold printed to give the proper angle to the subhorizontal joints. Then we cut the horizontal joints, and to finish and conclude, we have the sample of them here in the next slide, and we are going to see the different samples used in this study. We have 38 to 84 millimeters, like in the past study. We don't use the 30 millimeters. And at the left, we are looking the 1+2 with one subvertical joint and two subhorizontal joints, and the 2+3, that means two subvertical joints and three horizontal joints. Yeah, the triaxial test system, it was the same as the past part, with the different Hooke cells used and the corresponding sleeves. And as I commented before, we performed 97 triaxial tests for intact and 72 tests for jointed 1+2 and 69 for 2+3. So we obtained a total number of 238 triaxial tests. At the right, we can compare a typical strain curve of an intact. In this case, for intact, we used to measure the deformations strain gauges and LVDTs, but in this case, for the jointed specimens, we only use the LVDTs. Because if we attach a strain gauge into a piece, it will not give us a realistic measure of the strain. It will give us a strain measure of the rock part, not the whole specimen. So here we can see the different average result for each sample diameter and confining pressure. For intact, for jointed 1+2 and 2+3, sorry. As we can see, when we increase the confining pressure, also we can see that the strength increase for peak strength. And here we can see for in this case for the jointed 2+3 and 1+3 that there is a very little descending trend for the peak strength. Also for the residual strength, we can see that it's also increased with increasing of the confining pressure, and we can see here that clearly the residual strength has barely affected by the size of the sample, and it has a slight affection by the level of jointed of the specimen. So we decided to use to interpret the results of peak and residual strength, the Hooke-Brown criterion for rock masses, because it has the ESA parameter that is closely related to the level of jointing. So we thought that it will give us a good interpretation of the results. So here we have the results obtained for each diameter, and we can see that for peak strength, the results obtained decrease with the increasing of level of jointing. That something that it's clearly remarkable is that for 84 millimeters, for large diameters, the level of jointings has less affection to the peak strength. So when we increase the diameter, the level of jointing tends to decrease. And for the residual strength, we see that the lower values are those obtained for the intact samples and for all the diameters. And we think that they are due to the energy released during the break, because the intact samples tend to accumulate more energy, they produce more damage. So we expect values of GSI lower than ones obtained for the jointed specimens. For the elastic parameters, we observe that for the joint modulus with the diameter, it more or less stay the same. There are no variation or a slight tendency to decrease. With the confining pressure, it tends to increase, but the clear trend is when we increase the level of jointing, the Jones modulus tend to decrease. The more scatter position ratio tends to be more or less constant with the increasing of the diameter. It has a slightly descending trend with the increase of the confining pressure, and it seems to keep constant with the increasing of level of joint. Moving through the failure patterns, we can see the same patterns obtained in the intact ones, moving through low confining pressures that we have obtained axial splitting through the shear band for hard confining pressures. And we have found this for all the different sizes. So to conclude, to predict the strengths, the models USL and USL should show good agreement with experimental data. We observe the double trend, and this analysis suggests that we can introduce a side dependency on the Hook-Barn criterion. For the jointed section, the reduction of the strength is based on two main factors: the presence of joints and the increasing diameter. And regarding to the elastic parameters, we can say that the joint modulus tended to decrease, and the more scatter position ratio tends to be constant. These two words you can see in the published papers for the granite intact ones in the rock mechanics and rock engineering, and for the fissure and granite in the International Journal of Rock Mechanics and Mining Science. So thank you for your attention. This is the end of the presentation.
Congratulations, Manuel, for the clarity. And also, I had already listened to some of your work, but I'm always astonished by the number of experimental tests that you've been doing during your PhD. It's amazing, really. So yeah, thank you very much. So I would open again the Q&A session. So I ask if there is any question for Manuel. I cannot see. Well, maybe. Okay. Ailie Serasa. Yes, please.
Hello, it's me again, Ailie. Thank you for the presentation. I have a very simple question on the methods of the determination of your UCS. Is there any specific reason why loading rate is not considered for this particular research? Because I think we know that big size specimens, when they are tested under the same control loading rate, okay, they will have lower deformation rates, and that will give us lower UCS value. So that was my first question regarding the loading. And also question number 2 is based on the stress regime. So when I look into the value of stresses, it ranges from as small as 0.2 to 15 megapascal. So is there any possibility to kind of like classify them into low stress regime and high stress regime? So a little bit of clarification is needed here, because I practice geomechanics in the oil and gas industry, basically. So this would kind of like benefit to my understanding. Thank you.
Okay, first the first question. We use the ISRM suggested method for triaxial testing because we have that thing that I have to clarify. It's the we use 0.2 megapascal of confining pressure, both in intact and in jointed, because if you perform a triaxial test without the confining pressure with the jointed ones, you will have the part split and you have no test. So we focus on obtaining the peak strength in between the 5 to 10 minutes of the test. It appears on the ISRM suggested method. So we use the deformation control, and we more or less, because we have a lot of data of this granite, because we have performed so many studies that more or less we know when it will to fail the sample. And the second question, if I understand well, it was because you said that 50 megapascals is a lower pressure, or you can make again the question, pressure.
Stress regime. Are you considering 0.2 megapascal until 15 megapascal as a single stress regime, which is low or high, or is there any possibility to kind of like classify a certain value as low and also high stress regime?
Okay, I understand now.
Yes, thank you.
Yeah, we consider in between 0 to 5 megapascals low confining pressures, ranging from this 5, or you can see 7.5 to 10 mid confining, and 12.5 to 15 high confining pressures. We in our laboratory consider that, and we consider that kind of confining pressures because we consider that 15 megapascal, it will be more or less the same pressure that we will find on a mine, on an usual mine in our region. Okay.
Thank you for the clarification. Appreciate it.
You're welcome.
Good. Any other comment? Okay, maybe I can ask a curiosity, Manu, because maybe you said it, but I missed it. I could not get what is the physical reason of the ascending trend that we see at low confinements.
Yes. Okay, I'm going to.
Yeah, thank you.
Yeah, we are going to this part. Okay, this ascending part is due to the grain size. Okay, we consider this part the recommendation of the ISRM to perform a test. It's that the diameter of the sample, it should be at least 10 times the grain size. So when we have this such a large grain size, like we can see here we have 6 millimeters of quartz grain sizes. You can obtain a premature breakage for this grain size boundary. So when you have these small samples of 30 millimeters or 38 millimeters, you will have the failure to the grain size. And the other part, it's due to the weak lean theory that you say that it's more likely to have a failure if you have more surface to have a failure, also to have a defect.
Sure.
So,
okay.
in
Thank
a
you very
quick
much.
explanation.
No, but it's clear. Yeah, it's clear. Thank you very much. Any other question? Lina. Yeah, first there is a question about by Eliane Cabot asking if you can reshare the paper references in the last slide. Well, second last slide.
Okay, I'm going to.
Well, maybe then the video, if I remember well, on YouTube will be available again, so people can go and exactly this one.
It's better. You can see here on my slide because.
Yeah. Oops.
Okay.
And then there is a question by Lina Guayacan Carillo. By the way, I forgot to thank also, I mean, Felipe and I are chairing this session, but behind this session, there are other people. Ignacio, who asked the question before, Ignacio Perez Rey, also Lina Guayacan Carillo, and Federico Vagnona. I forgot to thank them as well. They, of course, helped with the organization. So yeah, Lina says we see a lot of variation in the results obtained in laboratory tests, especially for the artificially jointed rock. So based on your feedback, do you see any areas for improvement for future tests? For example, the preparation of the samples or in the test protocol?
There are areas for improvement. For example, in the making of the process of making the samples preparation, because you have to be very careful. I can tell you that, for example, for the 38 millimeter diameter, we performed 25 tests, but I prepared near for 60 samples that were not usable. So I prepared in total 90 samples. So it's time consuming, and the variation also, if I show you here I don't have all the samples. No, yeah, I have it. I have all the results for the intact ones. So you also have a variation in the intact one that we can say that it's due to the natural variability of the rock. We can say that more or less they are in the same range, that something expectable. So, but I can say that for preparation, we have an improvement area.
Okay, great. So I think we have to move on. So thank you very much once again, Manuel, for your presentation. Wonderful work. So I leave the word to Philippe now.
Yeah, thank you, Alessandra. So I will have the pleasure to chair the next two presentations. So the upcoming speaker, I will share my screen. So the upcoming speaker, speaker number 3, is Dr. Etienne Lavoine, who is an engineer specialized in numerical modeling applied to geomechanics and hydrogeology, and currently working for the company Itasca. His research experience has led him to work on the modeling of fractured media and the characterization of their hydraulic and mechanical properties. And currently he's working as a consultant, where he's focusing on various civil engineering projects. And for example, including also the study of the long-term behavior of nuclear waste underground repositories. And today's talk that we will show you in a moment is entitled Using Synthetic Rock Mass and Discrete Fracture Network Approaches to Study Rock Mass Strength Properties. So with that, I want to invite you, Etienne, to share your screen. I will stop at 9. Just a second.
Okay, can you see my screen?
Yes.
Great. Okay. Thanks for the nice introduction. First of all, I would like to say thanks all my colleagues, so Caroline Darcel, Philippe Davy, and also Diego Masivas and Hossein Kazani, because this work is funded by their company, SKB and NWMO, which are the nuclear waste agencies for both Sweden and Canada. So I'm going to present you some work we did on synthetic rock mass and discrete fracture network approaches applied to study fractured rock mass properties, including elastic but also strength properties. And I will focus on strength properties during this talk. Just okay. First of all, this work is in the context of nuclear waste storage. And when you deal with nuclear waste storage, you have to choose an earthwork to deal as a geological barrier. And often you have the choice with salt, for example, as we have seen in the first presentation, but very often with shales or crystalline rocks. And here we will focus on crystalline rocks. And crystalline rocks, they have the advantage to be quite stiff, to be quite have a large strength, and to be quite impermeable, but if they are intact. And the problem is that very often you have natural fractures. So you have huge networks that you cannot really see on the field if you go at the top, at the surface, or even deep underground. This is possible to map. And the problem is that these fractures are controlling the hydrogeological and the geomechanical behavior of the fractured rock mass. So the challenge with this type of crystalline rocks is really the challenge of natural fracture networks. And you have to deal with the challenge of scales, because these fracture networks are always multi-scale fracture networks, meaning that you have fractures going from the centimeter to the kilometer scale. And if you look at this kind of map, you see that you have a lot of small fractures and few large fractures, and all of them may be relevant to consider depending on the process happening. So the problem is that because you have this kind of large size distribution of the fracture, you may not have a characteristic length, and the question of the existence of a representative elementary volume arise. And also, as always, when dealing with fractured rock mass, you have to deal with the problem of anisotropy, because you may have different fracture sets with different orientation distributions. So our goal here in this project is to quantitatively assess the relationship between the pre-existing fractures, so natural fractures, and rock mass effective properties, including elasticity and strength. And I will focus mostly on strength here. And use it to develop a prediction workflow when classical rock mass classification systems assumptions are not applicable, and also understand the underlying physics of that relate the fractures to the properties of the fractured rock mass. So to do so, we base our analysis on numerical simulation using the synthetic rock mass, but also using a discrete representation of the fractured rock mass based on the discrete fracture network approach. So all these concepts are going to be developed just after here. So it is widely accepted that fractures decrease the strength of rock masses in comparison to intact rock. We have seen that just before in the second talk. And very often we rely to empirical approaches using rock mass classification systems such as GSI, for example, which is based on quantitative and qualitative observation that you have on the field or on the lab, depending on the fracture parameters, for example. So this may be limited when you want to apply it to in situ scales on fracture anisotropy. And this is adapted to heavily jointed rock mass when you have really a block assembly. So as we can see on the picture on the left, this is a picture that we are all used to see. And as soon as you have an assembly of blocks made by several sets of potentially infinite fractures, the density of the fracture network is only defined by the fracture spacing only. So it is applicable only when the model resolution is larger than this spacing. And then because of this spacing, because of this block assembly, you have the possibility to have a representative elementary volume, which may not be the case in the kind of rocks that we are looking at in crystalline rocks, where you have a population of individual fractures, and you may not have these characteristics. So to study this kind of medium, we use the discrete fracture network approach. So in this approach, the fracture network mass is seen as a collection of fracture surfaces that we call the discrete fracture network that is embedded in an impervious elastic matrix. So a lot of physical concepts rely on the fracture themselves. And these fracture surfaces, they are defined by statistical distribution. And you have one statistical model, but you need several realizations. So for example, you go in the field, you take some data, so you have orientations data, you have size data, and then you create a conceptual model, a mathematical model, where you define different fracture sets, different statistical distribution for the orientation, but also the size distribution. So here you can see the size distribution that is fitted by a Poirot model, meaning that you have a lot more of small fractures than large fractures. And once you have this statistical model, you need to perform several realizations to quantify the uncertainty that is associated to such a model. And you have one of the most important things to consider with fracture work mass is the fracture density. And depending on the process at hand, it may be relevant to use different kinds of ways to quantify this density. And in 3D, the two main ways we have to consider density is fracture intensity, which we call P32, which is defined mathematically as a total fracture surface per unit volume. But you can also define fracture density using percolation parameter, which is defined mathematically as total excluded volume around the fracture per unit volume. So it is unitless, and it has been widely used in hydrogeology to characterize the connectivity of fracture network, because if this quantity is larger than a certain quantity that we call the percolation threshold, the network are statistically connected. So depending on what you are doing, it may be relevant to characterize density by both quantities. But then, since we are interested here in geomechanics, we need to simulate not only the fractures, but also the matrix that is playing a huge role here. So to do that, we use the synthetic rock mass approach, where we simulate the mechanical behavior of the jointing rock mass first by creating a GFN, several realization of GFN, covering a range of explored parameters, so several density, several different size distribution, different orientation distribution, so that we can study what aspect of the GFN is controlling the rock mass. And then once we have these fractures, we need to create a 3D model of the fracture rock mass. So we have the domain that is cut by the fracture in different blocks that are stick together, and we assign mechanical properties to the fracture and to the rock matrix. And then we perform numerical simulation, numerical simulation of loading. So this is a test, just like in the presentation before, but this time this is done numerically. And we can just after analyze the mechanical response, such as the macroscopic behavior, macroscopic stress, strain, but also what happens inside. So you are able to access to the stress at every point of the model. So you are able, for example, like in this study, to study the stress fluctuations associated to such a medium. So the first phase of this work was to derive effective elastic properties from this approach. It started years ago. Everything is summed up in this paper from a Journal of Geophysical Research. And what we found out finally is that we were able to derive elastic properties, effective elastic properties based on a DFN approach, because given a DFN, we are able to recover with a semi-analytical solution the displacement that happens on the fracture. And we're able to quantify the contribution of each fracture depending on its orientation, depending on the loading of the mechanical parameters, the contribution to the total deformation, and accounting for interactions because we consider that each fracture see an effective medium. And one of the biggest conclusion of that work was that multi-scale DFN potentially display endless scale effect on elastic property. So here on the graph, you can see the evolution of the Young modulus with percolation parameter characterizing the fracture density. And you can see that this decreases exponentially with percolation parameter if you consider that you have fractures that are frictionless. So here, Ks is the shear stiffness, meaning that you have no friction here. But as soon as you increase friction, the rock behaves differently. And what we found out is that the ratio between the fracture and the matrix stiffness, so the ratio between the shear stiffness and the Young modulus, which is homogeneous to a length, is critical for the extent of the scale effect. And then you introduce this kind of characteristic length that I was talking about just before. So depending on the ratio between the size of the fractures and the size of this characteristic length, of this matrix fracture to stiffness length, the effective properties are driven either by P32 or percolation. But if you are interested, you can just have a look at this paper. Here we're interested more in strength properties, and to do that, we need to be able to simulate damage. And to do that, we use the bonded block model approach using the Itasca software 3D, where the rock is modeled as a bonded polyhedral element. So here we model the matrix as an assembly of tetrahedral bonded blocks, meaning that the blocks are stick together. So the blocks, if I zoom in and have a schematic view here, the blocks are deformable and they are stick together with friction, what we call subcontact that may break or not. And we also embed the fractures in this kind of model. So the fractures are represented by overprinting cuts on the intersecting blocks, so that in the end, you end up with subcontacts that are assigned matrix properties and fracture subcontact that are assigned fracture properties. And the matrix subcontact may fail if the stress is sufficiently high, and then the fracture properties are assigned to this subcontact that we call a crack subcontact. So the rock damage is captured by the rupture of intact subcontact. So to study that, we covered a wide range of parameters for our DFN analysis. We performed UCS and tensile numerical tests on 120 synthetic rock mass specimens generated from various DFN. So we performed analysis on constant size distribution. So here, all fractures have the same size, here, 2 and 1. And also with poor low fracture size distribution with different exponents, meaning that you have more or less large fractures than small fractures. Well, in what I will show you, fractures are assumed to be frictionless, so the shear stiffness is equal to 0, because it was easier to start with that, because the displacement on the fracture is more important, that it's easier to analyze everything. And further work is ongoing to study the impact of fracture friction properties on the strength of the fracture mass. So we need to characterize damage to make our analysis, and to do that we have macroscopic but also fracture scale indicators. So about macroscopic indicators, we obtain stress strain curve by measuring the macroscopic and stress and strain on the sample. So we're able to recover the effective Young modulus, the peak stress and the peak strain. And we also record the increment of fracture density by measuring the increment of fracture surface, because each time a subcontact breaks, we are able to recover the associated value of surface in the model. And we also have the possibility, because this is numerical analysis, to perform more specific analysis using fracture scale indicator with an indicator that we call PM that we developed, that is defined, that can be defined from subcontact that belongs to all fracture, and that is a function of the fracture displacement multiplied by the fracture surface divided by the macroscopic strain. Meaning that once again we obtain a dimensionless measure, and this because if you are in the elastic regime, this is constant, because the more you apply stress or strain on your sample, the more you increase the displacement on the fracture, and this is proportional to the applied stress or strain. So this is constant, but as soon as you derive from this constant value, you are able to say, okay, I'm creating some damage here because we are not in the elastic regime anymore. This is what we can see here on this kind of test, which is a tensile test with few fractures. You can see here the blue dots are the subcontact that belong to the fracture with fracture properties, and in red you have the subcontact from the matrix that failed to become crack subcontact. And each line here represents the fracture contribution to the global PM value. And you can see that in the elastic regime, all the values are constant, but as soon as I start to break around the fracture, this value is increasing, and increasing a lot in the end, because the damage is progressing quite fast. So what we can see here is that the fracture that has the highest amount of energy, that is quantified with the PM parameter at the beginning of the simulation, is responsible for damage initiation. So here, because the fracture is almost horizontal, the loading on the fracture is quite important, and we have the highest amount of energy, so the highest amount of stress redistribution around there, and the matrix start to break around this fracture. So this is what we call the critical fracture. But depending on the network, this is not always the same fracture. So, for example, another fracture wins the race because the geometrical configuration enhance the energy on that fracture. And if we look now at some results on UCS and considering macroscopic indicators, we can see that also this parameter PM is controlling the strength of the sample. So what we show here is that we show the peak stress normalized by the initial value as a function of the initial PM parameter, so the total energy associated to the system. And what we can see is that we have an exponential decrease with this parameter, and that the fracture size has an impact. So if we look at the fracture here at the simulation in blue, so each dot corresponds to one test. In blue, in dark blue, and light blue, this corresponds to the constant fracture size DFN. You can see that the peak stress is lower for fractures that are larger. So for the blue, the white, the clear blue dots, because the fractures are larger. If we now look at it in a different way, here we show still the normalized peak stress value as a function of the normalized Young modulus. So if you have a smaller Young modulus, it means that you increase the fracture density. We can see that all the dots are quite well distributed on this kind of curves, and that you have a sudden and intense peak stress decrease with the addition of a few fractures, while the Young modulus slowly decreases. Meaning that as soon as you introduce a small defect, a small fracture, you will create a huge variation peak of strength in comparison to the intact sample. But we show also that for higher density, the strength decreases more progressively, almost linearly, and that's what we call the sudden rupture and the progressive rupture. So to conclude, we use the DFN SRM numerical setup for discrete fracture network and synthetic rock mass numerical setup to better understand the relationship between the pre-existing fractures, so the natural fracture, in multi-scale environments, and relate it to rock mass effective properties, both including elastic but also strength properties. This is still ongoing work on the strength properties. And what we have shown is that the fracture that has the highest amount of energy that we characterize with the parameter PM is responsible for the damage initiation, and that the strength of the fractured rock mass is strongly controlled by the initial value of PM, which is a mix between the fracture geometrical and the mechanical properties. So I hope it was clear enough. Thanks for your attention, and I will be really happy to answer questions and go back to a few slides if needed to go a little bit deeper in the subject. Thanks.
Thank you very much, Etienne. Very nice presentation, very complementary also to the last presentation that we had before from Manuel.
Yeah.
So if there are any questions, you could address them to Etienne. If not, I will start with the first one. I was quite interested about the general framework that you proposed, and for me it would be also quite interesting if you could take into account hydraulic properties in your model. I don't know if you have studied this or you have planned this. For example, if you have some loading and some deformation closing for fractures and then affect in this way the permeability, is this something that you can consider in your model?
This is not the topic here. You mean that considering that you have fluid flow or the
Yes,
impact?
like for hydromechanical couplings.
Yeah, hydromechanical coupling. This is not done here, but this would be obviously interesting. But this is already quite complex to understand. First the mechanics, but maybe
sure.
So the first phase was elasticity. The second phase is strength. Maybe the third phase will be hydromechanical properties. This would be an interesting project, but still we have another project that we call permeability, where we are trying to link the impact between the stress and the permeability of the network, but not using the synthetic rock mass approach.
Okay, thanks. Have any questions? Otherwise, I have a second one.
Yeah.
Because you showed in one slide quickly the power law, your fracture distribution, fracture size. So now I'm wondering, is there any limit or any boundary up to which resolution you need to model your fractures? Can you stop at certain size?
Yeah, this is always the big question. For the maximum size, you can consider that you will limit to the size of your domain, and the more you increase, because of the polar nature, you have less and less fractures, big fractures. But this is also always the big question where you should stop for the smallest fracture. For example, here you can see that the distribution is going down here, but it's very often because of resolution techniques that don't allow you to account for smaller fractures. But obviously, you will not consider fractures from nanometer scale, otherwise you will have billions of fractures. But the idea of this kind of approach is also to understand what are the most important fracture depending on the process at hand. Either of this is really what we call the discrete fracture network methodology, is to understand what are the fractures depending on a process at hand. It can be hydrogeology or geomechanical subject. What are the fractures that matters in fact? Is it the small one or the largest one? So we use numerical simulation as a support to have a better understanding of that kind of system and find what are the relevant structures before going into a more deep modeling of any kind of system.
Okay, thank you very much. Do we have another question from the audience in the meantime? Yes, there's one from the chat from Lina. She's asking how long does it take to implement and calculate such a model?
Yeah, to implement, it's a research project, so it's always a long process where you go back and you relaunch everything. So it's months, years, but because it was done and it was created for that kind of analysis. But to calculate such a model, it depends on the number of fractures that you have and the resolution, because the more small blocks that you have to represent your matrix, the more computational time it takes. So for that kind of model, where we are able to go to few hundreds of fractures, and I don't remember the number of blocks that we have here, but we have an idea of the resolution. This can turn between 1 or 2, 3 days on a huge computer. It's quite computationally intensive, and obviously it depends on many parameters such as the friction parameters, because if you have more friction on the fractures, you will need to load a larger amount of time to reach the strength of the simulation. But yeah, the idea is 1 to few days for one simulation. So it's quite a long process, given the fact that we want to cover hundreds of simulation. I said that I had 120 synthetic rock mass specimen, but now that I have a new parameter that is the frictional properties, I need thousands of simulations to make analysis, so it's quite complicated. Thanks for the question.
Okay, if there are no more questions, I think you can move on to the next speaker. Thanks again, Etienne, for the very interesting work.
Thanks.
And show my screen. So last but not least, we will have a talk by Jorge Terron-Almenara, and Jorge is holding a Master of Science in Geology obtained by the University of Granada in 2008, where he has specialized in rock engineering, tunneling, and underground works, with a master program organized by the UNED and the AITOS in Spain in 2009. And since 2010, he is working in consultancy and as an engineering geologist, where he has been mostly involved in tunneling projects in difficult underground conditions. Since 2020, he is working on his PhD with the topic tunnel rock support design in poor ground conditions, in which the current traditional design practice used in hard rock tunneling is investigated. Here the aim is to find scientific background as to develop new design recommendations or procedures which should help to derive more optimal support designs in poor ground conditions. So today he will present his talk, which is entitled A Hybrid Approach for Adequate Rock Support Design in Hard Rock Tunneling. So Jorge, I would stop my screen sharing and invite you to share yours.
Hello, hello everyone. I think you can see my screen now.
Yes, can you start the full screen? Yes. Perfect.
Yeah, hello everyone, and thank you, Philip, for your kind presentation, and thank you for the ISRM to inviting me for this ISRM joint webinar series. I also appreciate that the ISRM is still considering 40 years old people as young people, so I double thank you for this. As you can see, I'm doing the PhD at NTNU in Norway. I am right now at the very, very end of my PhD, so we have a significant amount of results and conclusions. But we have 20 minutes only, so I will try to summarize as much as possible. And I will just present a part of the PhD, unfortunately, which is today the topic, as you say, Philip, is the hybrid approach for adequate rock support design in hard rock tunnels. So we'll focus on poor ground conditions. As you can see in the background of this first slide, we have the RRS. Maybe you have heard about it before, which is the way we support permanently tunnels in Norway with ribs of reinforced shotcretes. That's why we say RRS. So I come back to that later. And before I go into the details, I would like to present the team or the research group. First, we have Carl Gunnar, which is my supervisor working at NTNU and also at NGI. Are Hobart, he is my co-supervisor working at the rock authorities in Norway. We have Charlie, which is my co-supervisor, professor in rock mechanics at NTNU. And also to the top right, we have a constellation of sponsors. First is NTNU, the university where I'm doing the PhD. We have the road authorities, Statens vegvesen. We have the railway administration, Bane NOR. We have the Norwegian Tunneling Society, NFF. And then we have also my current company I'm working for in parallel to the PhD, Sweco. To the bottom right is the picture of master students working in the field. It's a small tribute for them because without them, I don't think I could complete my PhD because they are doing an excellent job compiling and sampling and doing tests. So a small tribute also for them. As you know, in Norway and also in Scandinavia, we have hard rock conditions, competent rock, crystalline rock, almost everywhere. Evidence for that is the high cliffs and the steep cliffs you can see in touristic places like those two to the right-hand side. And also this pyramid top or mountain in the middle of Norway. An evidence of hard and competent rock is one of the longest, I think it still holds the title of the longest roadway tunnel, the Elham tunnel, with 24.5 kilometers. In this part of the tunnel, where you have one niche at each side, and the tunnel span is about 25 meters, and still is supported with only rock bolts and shotcrete. So you can imagine, in general, we have a good and competent rock. However, we do also have poor ground conditions, like this weakness zone that came into a collapse. This is in the Hanekleif tunnel. And the collapse happened, fortunately, in Christmas Eve, so no one was injured. But the interesting thing here is also that the collapse took place after 5 years in operation, that the tunnel was with traffic. One of the reasons for that was that despite that the weakness zone was identified during construction, the long-term behavior of the infilling holding those blocks that you can see on the tunnel inverts weakened. The strength characteristics weaken over time. So this was not captured by the empirical classification methods that were used at that time for the design of support. So this is a more recent case in the northern of Norway in 2020. It's a tunnel with laminated rock mass, very hard rock, meta sandstones with up to 200 to 250 megapascals. But you can see it's very well laminated, close spacing, and also some cross jointing. So despite of the heavy support with the mentioned RRS support, we got actually this failure. Flexure failure in the top part. So that was an interesting case for us. So we therefore came to study this case as part of my PhD. So I'm coming back later on into this. We do also have other cases, not in Norway, but in this case in Albania, where I was working for several years, where we implemented both the principles of hard rock engineering for tunnel, like we use in Norway, with permanent support based on shotcrete and bolts. And we did also include or implement the principles of weak ground engineering for tunnels, like, for example, deformation monitoring and the convergence confinement methods and more elaborated design work. So after 5 years, this tunnel is in place, no collapses, no failures. And at the end, the PhD is very much focused in this because we observed that this approach is working when you involve several methodologies. So you don't actually need to have either black or white or a weak ground engineering or hard rock engineering like we do in Norway. You can actually involve several methods. So this is the basis of the hybrid approach that I am going to present today. So a bit on the motivation, if we look on the number of kilometers that Norway builds of tunnel each year, it goes, of course, up and down depending on the politicians and so on, but in average we have about 60 kilometers of tunnels each year. According to some literature and experience, about 5 to 10% of those tunnels are constructed in poor ground conditions requiring heavy support. So that means 3 to 6 kilometers each year of tunnel each year are built in poor ground conditions. So we look on this publication from Høyen et al. Up to 50% of optimization could happen in the design of permanent support in those 3 to 6 kilometers. That means that we have a potential to save about 1,500 to 3,000 of heavy tunnel support each year in Norway. So there is obviously a good motivation, not only economic, but also the potential save in construction time and obviously the save of carbon footprint emissions. If we look on the design principles in Norway for rock support design, basically we use the rock mass as a bearing construction. So we normally implement rock reinforcement with rock bolts and shotcrete so that we keep the blocks in place. And as long as the rock is in place, then a rock arch can be formed or generated around the tunnel. So basically it's the rock mass that takes the loads. The way we design this rock reinforcement is first by doing an assessment and a mapping of the rock mass at the face, like you can see in this barrel. Then we classify the rock mass based on the Q system. And then we come up with an empirical rock support design. This design is permanent, is final. And in addition to that, we observe the tunnel, but very seldomly we need additional support. So basically these principles are based on the following. So in the first graph to the top, you have to the left massive rock, and the more to the right, the more joints and more weak rock. So the weak rock or weak infillings in joints are represented by black color. So basically what I said before is that in jointed rock, you only need rock reinforcement, basically, to actually keep rock blocks in place so that a natural arch or a pressure arch is formed. So then it's the rock mass that takes the load. However, when we go into more weak rock or the poorer rock masses or poor ground conditions, then the rock mass cannot take that much load, so much of the load is transferred then to the rock support. So then we use what we call load-bearing support. And in Norway, this load-bearing support is with RRS, as I showed you in the first slide. So how we do design of permanent support in Norway basically is, as I said, based on the queue system, but we use this table. This is in the guidelines from the Norwegian rock authorities. So basically, you divide the rock mass according to classes, and those classes are depending on the Q value, and depending on those classes, you extrapolate and get into a support class. So the first 4 rows, or first from A to E, so you actually have rock reinforcement in the form of rock bolts and shotcrete only. And it's a clear division at Q value 0.2, where you start using load-bearing support with RRS, as you can read here. So as you can see, it's a very simplified version if you compare to the Q system. And this has been used for the last 15, 20 years. So what we try to do in our PhD is to focus, in this part where we are in this question mark area, where we try to figure out a new approach that can better describe the rock mass conditions there, and therefore to get a better, a more adequate design. So coming back a little bit on the Norwegian approach, is basically shotcrete applied at the face as permanent support, and rock bolts fully grouted as permanent support. In areas with poor ground conditions where you need load-bearing support, so you actually need, we actually install the RRS, which is basically those beams of shotcrete installed circumferentially to the tunnel, and then reinforced with steel. So if you adjust the center spacing of those beams, or also the amount of steel reinforcement or the thickness of those beams, you can adjust the load, you can adjust the design to the load conditions at the face. So it's a very simple way of design, but it has been working quite okay during the last years, besides the failures that I just showed you. So the objectives of the research was, I can summarize on those 3. First was to identify in which ground conditions rock reinforcement and load-bearing support are necessary. Basically is to go from the current support strategy, as you can see in the top right figure, to this figure in the top, in the bottom right. So we need to define in which conditions we may like to implement a different procedure, in this case a hybrid approach. So the second is to develop that hybrid approach, and the number 3 is to estimate how much save or rock support can we optimize with this hybrid procedure. So here in this slide, I'm showing you the general methodology from 1 to 5. I was very lucky that my co-supervisor is working at the rock authority, so I got hundreds of case records. But I had to filter and sort all of them, because we need the research on the PhD is focusing on poor ground conditions. So the criteria was to basically use rock mass conditions with the Q value below 1, and also case records of recent tunnels. And the reason was that old road tunnels in Norway are also designed empirically, but some modifications came in the guidelines in Norway after from some 10, 15 years ago. So another criteria was cases where we had available deformation monitoring results, because then this will allow us for numerical calibration of the input parameters. And also other criteria was that those case records had sufficient and quality information about in situ stresses and the properties of the rock mass. So the second step, was rock mass characterization. Most of the rock masses were already characterized, but in some other cases we had to take samples and test them, and that's why I took this tribute to the master students also. So step number 2, I have done part of it, but also master students. Step number 3 was to model all of those cases all of the 118 case records and calibrate all of them numerically. So that was a big job. That took about half a year to model all of them and to get reasonable results according to the deformation monitoring. So once we had calibrated all the models, then we went to step number 4, which is the central part of the study, which is basically to study the performance of the different design methodologies that we use nowadays in rock tunneling, which is the empirical method, the numerical method, and, for example, the analytical method with convergence confinement method. The second part was to analyze the loads on the support. That was done on the basis of support pressure, moment loading on the shotcrete support, shear loading on the shotcrete support, and bolt loading. We were also looking to the rock arching, and I will show you a good example of that afterwards. And finally, we went to look into the effects of rock mass properties on ground behavior. So from the results of these 3 elements of these 3 boxes, we plotted all of the results in different ways to try to find correlations. We indeed found some correlations, but the first observation was actually that there was indeed a nice correlation that in each of those, what we call ground behavior types, the performance of the empirical or traditional way using the Q system in Norway vary. So the first we did was to divide or to split those 118 cases in ground behavior types. So maybe you have seen in the Austrian Geomechanical Society that they have a very large table, I think 13 or 14 cases with ground behavior types. So we have done something similar, but much more simple and also adjusted to the Norwegian hard rock conditions. So basically we have 5 in this slide. We have a 6th one, which is swelling conditions. But to simplify today, I just included those 5. So looking into the numerical results, I wanted to first plot the performance of those 3 main design methodologies: numerical, analytical, and empirical. And the first figure A, you can see all of the results from the 118 cases plotted in the same graph. As you can see, there is an approximately good agreement in the results of tunnel strain in between Q value 0.1 and approximately 1 or a bit above 1. When we move on to weak rock masses, that can be, for example, in large fault zones in Norway. There's also a good correlation up to 0.1, but below 0.1 is a bad correlation. However, when it's not the same as when we plot all the cases, because when we reach Q about 0.6, 0.7, this agreement or this overlap is missing. So there is, in fact, a difference in the behavior and also in the performance of those design methodologies on how they capture or prognose tunnel deformation. If we move to figure C, in hard and jointed hard rock masses, then the good agreement actually happens from Q value 0.2 or 0.3, and then down to, well, we have no more results, but we are down to, let's say, Q value 2 or 3. So we already observe a difference between the weak rock mass and hard and fractured rock mass. If we move to D, which is the anisotropic rock masses, that means the rock masses with a preferential joint direction, like, for example, webbing or lamination. Then there is almost no agreement. Some agreement can be observed perhaps from Q value 1 and above 1, but in fact, I don't think Q system would be very nice to prognose tunnel strain or tunnel deformation. in laminated rock masses. So the same we did with tunnels with low rock stresses and in weakness zones. But for those two last cases, we had less case records. So the representativity here is less for case E and F. So if we put the previous results also in terms of loading on the support, in this case, factor safety of for the moment in the chocolate support as a function of the Q value in the x-axis. We see for all of the colored dots, except for the gray colored ones, we see that factor safety between 1.5 and 2, which is quite reasonable for tunnel engineering, is obtained for Q values below 0.1. But above 0.1, we kind of start seeing some spread. And that for us is telling that the Q system is okay, it's working reasonably okay for Q values below 0.1, but above that, we have this transition zone that I mentioned before, where we need another type of approaches. The gray dots, they're actually dots representing the anisotropic rock masses, or better say, the rock support in anisotropic rock masses. And they have an opposite. The trend is opposite. And the reason for that is that much of the heavy support is used in this case to hold the vault spiling in laminated or horizontally layered rock masses in Norway. Not necessarily to hold the rock load, but to hold the vault spiles. So that's why you get such a huge factor of safety, and also in an opposite direction to the others. Some other results, now looking into an empirical approach based on Barton et al. In this graph. It is modified from Barton et al. 1974. The gray shadowed envelope is actually showing the best estimate of rock load based on Q values on G air, which is the joint roughness number. So we did an exercise of plotting those 118 cases also in this empirical graph. And we actually see a similar tendency as we saw in the numerical approach. That, for example, in this case, from 0.01 to actually to Q value 2 and 3, the rock support pressure of the installed support is very much above and increasing towards the right-hand side of the graph. So at some point, actually in this empirical graph, at some point, we have a mismatch with the numerical calculations where we say it's 0.1, but it's also clearly indicating that we are using too conservative design in Norway. So if we look on the tunnel strain or tunnel deformations calculated empirically with this formula of Barton et al. 1974, Q divided by the span, you get the dots, the blue dots, and also the triangular gray dots plotted here, which is quite linear because of the graph is plotted in exponentially. But if we plot the actual calculations we did with the numerical analysis, the gray dots and the black triangles, you actually see a mismatch. Actually, if you see, for example, a 10% of tunnel strain in a 10-meter span tunnel would be 1 meter of deformation. We very seldom, or I would say almost impossible to see that deformation in Norwegian tunnels unless you have a tunnel block failure. But then it's a collapse. It's not a plain deformation of the rock mass. So it's a different behavior. So again, from 0.1 to approximately Q value 2 or 3, you have a good match for predicting tunnel strain with the Q value compared to numerical and analytical approaches. So I could show you more results, but as long as we have only 20 minutes, I just show you these ones. And based on those results, we evaluated the performance or the ability of these main three design methodologies to perform different, so to say, characteristics, like, for example, to the evaluation of factor safety and the support. The appropriateness of the support design can be evaluated, yes or no, or the consideration of other tunnel geometries than other than circular. So we did this kind of matrix that is then implemented into the next slide I will show you. So this is how it looks like, the hybrid approach. So basically, you have these 6 main types of ground behavior types in Norway. When you have selected one representing the tunnel conditions you have at the face, then you evaluate the loading and failure mechanisms. This is done empirically. I didn't come today into the details for that, but you can read into the more details in the paper. I will give you the links afterwards. And then the idea is that you move vertically through the columns once you have selected the ground behavior type. So I don't intend you to read in detail here right now, but the thing is that you get different recommendations in a kind of a guideline. So you start from some recommendations regarding site investigations. Then you get also some recommendations for how to use the empirical methodology, not only the Q system, but also the GSI and RMR, and also analytical methods, numerical methods, and how you would like to use monitoring results. So based on all these methodologies and recommendations, and then you have a recommendation for the support design. So it looks a bit complex, but the way we constructed it was quite simple, so that it can cover as much ground conditions as possible. So we have already published 2 articles. One of the results are in these slides. Is in the direct application of this hybrid approach in layered rock masses. This is the same tunnel I showed you before with a failure in the roof. And then we conducted the hybrid approach, and among others, we conducted UDEC calculations. And then we compared the traditional or the current practice for rock support design in Norway compared to the hybrid approach. So that's why we have gray color columns and shadowed columns. And then in this graph is representing the consumption of support, so because we wanted to compare the costs of the consumption of support. So we, in fact, observed some variations. So basically, the support is conservative, and the potential save in economic save was 0.3 million euros in just 175 meters of tunnel. It might look like very little amount of money in the context of tunnel construction, but in terms of the reduction of possibilities or the reduction of risk to tunnel collapses and failures, like this one I show you, that is much more costly. So this 0.3 million euros is not representing this failure, obviously. So this is one case, and the other case is the application of this hybrid approach in low overburden conditions. This is another tunnel in Norway with only 6 to 7 meters of rock overburden, and also with some buildings on top. So we conducted some numerical calculations, and we implemented a hybrid approach. We in fact observed that yes, the rock boards are loaded to approximately half of their capacity, but the shotcrete support or the RRS support is very little loaded. This is moment loading, 4.4 kilonewtons meter. So that's why when you see on the figure C and D, you see a so high factor of safety on those support capacity diagrams, because the shotcrete support is not loaded. And the reason for that is you get the reason for that by looking at figure B, and is that the rock is arching. The rock blocks that defined by the joints are confined and also taking loads. The rock mass is taking loads and arching. And you can see from the green tonalities here in figure B is compressed, is the compressed part of the rock blocks. And you kind of see that rock arching is taking place. And then this is showing that rock is arching. So most of the load is taken by the rock mass, even though you have a relatively short rock cover body. So in this case, the total save, if we were to implement the hybrid approach, would be 0.4 million euros. It's not much again, but if you see all of the cases that are all of the kilometers tunnels built in Norway and in Scandinavia, so then it could be a lot of money. So moving to the conclusions, yes, it is possible to optimize and achieve more adequate designs of tunnel support in poor ground conditions in Norway. Such optimization can be found principally in rock masses of quality between 0, 1, and 1. In situ stresses and rock mass properties have a direct influence on the ground behavior, and this is normally not captured by empirical classification systems. And with the use of a hybrid approach, we have seen that it is possible to involve different methodologies. They are known and relatively old methodologies, some of them. But what we have presented is a new approach where we give recommendations for how to integrate all of them. So with this, I think the technical part of the presentation is done, but I wouldn't like to conclude without first marketing our next conference, which is the next ISRM International Symposium, EUROC 2025 in Trondheim in Norway. So the registration will not open until the 15th of January. But as long as I'm the co-chair of this conference, I didn't want to miss the opportunity to market this conference. So you have all the details on, about the program and so on in this website. So I will not go into details. But please try to have a look, and if you're interested, you can. We will be happy to answer some questions if you wish to visit us. So thank you for your attention. Here is the links of the 3 papers that we have published so far, and then I will be very happy to answer your questions. Thank you.
Thank you, Jorge. Had a very interesting talk. It was nice to see also some application examples that you showed. Since time is running short, we have time for maybe one short question. Yes, Matthias, you can speak.
Me? Yes. Hello. Sorry. Yeah. Thank you, Jorge, for this very interesting presentation. It's also very relevant for me. I introduce myself quickly. I am a rock engineer working on Sotrasambandet project. I don't know whether, I'm pretty sure you know, but just for the rest of the audience here, we are currently, I think, still the biggest issued road contract in Norway. We excavate more than 10 kilometers of road tunnel in total. And what we especially do is we excavate a lot of different profiles and geometry. My job is mainly here to optimize a lot also basically the support that we are using within the framework that we are bound to by the contract that we have right now. I have a lot of questions. Since we're running out of time, I don't want to steal too much of your time. Maybe just one quick question, Jorge, maybe your take. One thing is the geometry, the size of the openings that we have. The problem is, or I see the challenge here in Norway is especially that the practice is that the design is determined irrespective of the span, if you want, or the opening size of tunnels. My impression is that this has a very, very big influence, as you already presented, with confining stresses and so forth and so on. So not only the, let's say, the rock mass classification in that sense, the Q value, but also the size or the exact geometry of the opening do you have maybe a suggestion, or what is your, do you intend to work in the future on this parameter as well?
Yes, obviously, yeah, tunnel span has a great influence, a great impact on the final design, obviously on the tunnel behavior. This table, you have a good point, because this table, I forgot to mention that this table of rock support design recommendations from the Norwegian road authorities is for tunnels of up to, if I remember well, 12.5 meters of diameter. So
yeah.
Beyond that, you have to, well, they say you have to make a special design. Okay, but regarding our research, we have most of the tunnels we have picked up here. I also forgot to mention, so you have another good point. Most of the tunnels we have considered are between 7, 8 to 10, 11 meters of diameter. So, well, it could have some impact on the results, maybe, but I don't think it could be quite significant. So I don't think, this is at least the research we have done. So I don't know if I answer your question by that.
Yes,
but,
yes, absolutely. I mean, because I think this is personally from the experience that I see here, it's if we manage to decouple basically the design or the design of the rock support from the rock mass classification and put the step in between, we can obtain a lot of savings, because it makes a difference. Yes. That what we have to, whether you excavate a 5-meter diameter or a 24-meter diameter underground opening, and we are excavating in our project from 5 to 24 in the full range.
Yes, actually, I can tell you one of the reasons for this tunnel failure that you are seeing now was 2 short bolts installed in the roof, but they were according to these guidelines. So and this tunnel was actually on the limit for this what I told you, 12.5 meters. So that they used 4-meter long bolts in the roof when this happened.
Mm-hmm.
So it was actually on the limit to, or on the threshold to actually trigger on a special design according to the Norwegian guidelines. But since it was in the limit or on the threshold, they used what the guidelines said. Nothing wrong with that, but it didn't work, as you can see here, 4-meter long ones. So after that, they were using 5 meters, I think. This tunnel is, I think, 12.5 or 13 meters. That's why I say.
Okay, thank you again, Ignacio. Sorry, thank you again, Jorge. With that, I want to close this 15th ISRM Young Members Web Seminar. Again, on the behalf of the organizing committee, I would like to thank the ISRM for helping us in the organization of this event and for supporting us. I would like to thank again the organizing committee, so especially Ignacio Perez-Rey, Alessandra Insana, Federico Vagnon, and Lina Guayacan for organizing this event. Of course, I would also like to thank the speakers again. So today we had very interesting presentations of Dr. Elham Mahmoudi, Dr. Manuel Alejandro González Fernández, Dr. Etienne Lavoine, and Jorge Terron-Almenara. I think these were very interesting and valuable presentations, and we had different topics very relevant for rock mechanics and rock engineering. So I hope that the seminar had provided you some new insights and new challenges for your future research. And we hope that we can continue this periodic event for sharing ideas about rock mechanics and other related topics. So with that, I want to just share you some information for the next seminar. Of course, we haven't decided for the date yet, but just to notify you that it will be held in December. And please stay tuned for the exact date and the time, which still has to be confirmed. So keep up to date on the official channels, like on LinkedIn or on the internet through newsletters. So we hope to see you again on this date. And with that, I want to close the session. Thank you again.
Thank you very much.
Thank you.
Thank you
If
very
you're
much,
interested in
Philip,
participating,
and
contact
to all the
us.
moderators and speakers and attendees for an excellent seminar. See you soon.
Thank you, guys.
See you soon. Bye-bye.
Bye-bye.